Okay, so we are talking about firewater demand today. I'll try to go through it, then you can ask your questions afterwards, if that's okay with you. So essentially for firewater demand calculation, depends on the clients you're working for. Some clients are, they have their preferred way, which is that you provide water for all equipment, irrespective of the fire risk assessment. But a good number of clients, including CEPLAC, prefer that you do a form of fire hazard analysis for you to make sure that whatever you're providing water for is based on a scenario, an analysis that's been done. But you know, because of the way this project is running and we needed to meet up with time and all of that, I couldn't wait for the fire hazard analysis to be completed before I started the demand calculation. But it turns out that in this case, we had to provide protection for practically all the equipment anyway, because the fire hazard analysis shows that if one equipment is on fire, because of the layout, practically everything around it has to be cooled, which is what I had already assumed anyway. But in some cases, depending on how your layout is, you may find out. So essentially what you're trying to do is to provide water, fire water, to cool any equipment surrounding an equipment that is on fire, so that the other ones, when you're cooling them, you're not applying the same water as you would have applied if you're trying to extinguish a fire. So there are standards that give us guidance on which application rates to use. And one of such standards, I believe, is API 2030. API 2030 will tell you, it will tell you, depending on the type of equipment you're dealing with, what should the application rate be if it is on fire versus if you're cooling it. So to answer the question about where application rates come from, depending on the customer you're dealing with, in some cases, some of the clients, they have their own standards that already give you these answers. But in this case that we're working with, we used international standards. So that's to answer one question. So anyway, when you're going through, you now have to define scenarios. So the first scenario I defined was assuming we have equipment, we have things in there. Sorry, I'm trying to. There's something I'm trying to do. Okay, so in this case, I divided the entire facility, the entire gas plant, into zones, and the zoning is based on the equipment that are closest to one another. So, for example, my first zone, what I called my first zone is the inlet manifold area. So the inlet manifold area zone has, I put the inlet manifold system, the feed preheater exchanger, the stabilizer feed flash drum, and the stabilized condensate pipeline pumps together in one zone. And that's because they are close enough to one another such that if one of the equipment is on fire, they are close enough for the other ones to need to be protected. So I did the division based on the plot plan. So it's the plot plan I was looking at. And so essentially, if you're going to have to do your fire zoning, there are no hard and fast rules. But essentially, you want to see equipment that are close enough to one another, such that, like if you're trying to describe to someone where the feed preheater exchanger is, you can easily say, oh, it's not too far from the inlet manifold. So you know that they are close enough for it to be that if one of them is on fire, the other one will need to be protected. So basically in zoning, which is one of the other things you want to do, because you cannot provide fire water such that if one equipment in the entire gas plant is burning, you want to be cooling every other thing. You'll be requiring more water than you actually need, because it's not every equipment that is at risk immediately because, for example, your inlet manifold system is on fire. But anyway, if your fire hazard analysis shows that the one that I'm thinking is extreme, for example, something in zone 2, let's say if the fire hazard analysis shows that for the AG compressor package could also be impacted by fire in the inlet manifold system area. There are two things we could do. We could still keep our zoning as is, and then we just say that, okay, so when there's a fire in zone 1, we also want because typically what you do to physically achieve the zoning that you have done in your theoretically is to provide deluge valves such that if you've made your system automated, which hopefully we are going to do, because in this case this is a gas plant. Sorry, please hold on. Please hold on a bit. Okay, apologies. Okay, so because in this case, what we're trying to achieve is a gas plant. So we don't want to put people, as much as possible, we don't want to put people in the line of fire, because if there's a fire from a gas, you can have a jet fire, and the jet fire goes really far, and the effects are worse than if you're dealing with a fire from a liquid hydrocarbon. So as much as possible, we don't want to have people in here if we don't need to put people. So we are going to do all we can to automate as much as possible, because it is a gas plant. If we're handling crude oil, there are some things we may be able to get away with that we will not be able to get away with because we are dealing with a gas plant. Or if we're handling condensate is something in between the crude oil and the gas. So you can still find some opportunities for manual operations. But because we are dealing with a gas plant, as much as possible, we don't want to put people in here if we don't have to. So we are going to set up our system such that once your fire and gas detectors detect, depending on how we decide to do it, but typically, probably if you get to up to about 20% of the lower explosive limit, your detectors will already begin to give the signal. And in some cases, like maybe by the time you're getting to 50% of your LEL, you begin to take executive action. And I think once there's a confirmed fire, which whatever the philosophy is for confirmed fire for this project, once we've confirmed that there's a fire in an area, the deluge valve in that area is going to be activated. And if we set it up such that it's that zone and the other zone that we want the deluge valves to go off in the event of confirmed fire, then that means we need to design for that. But we've currently just designed such that one zone, it's just one zone. Once there's a fire in one zone, then we need to provide protection for that zone. So our Firewater system demand is based on finding that zone that has the maximum water demand. And it's that zone that we're going to use as our design zone. So we are not going to add up from zones 1, 2, 3, 4, 5, and 6. No, we are just going to be comparing which of the zones has the highest firewater demand. And that's what's going to govern our firewater demand requirements. So I'll just take a bit of time to explain. So we have in this case, in this scenario 1, I've said assuming you have the inlet manifold system on fire. So you look at the equipment. I've looked for the equipment around this zone of the inlet manifold area. So I identified the inlet manifold, the feed preheater, exchanger, the stabilizer, feed flash drum, and the stabilized condensate pumps. So the first scenario is assuming we have the inlet manifold system on fire. We will still need to be cooling the other surrounding equipment. So I've got the dimensions for the inlet manifold system from, I think I got this one from what do you call it? I believe this one came from Seplat themselves. I can't remember, or if it came from someone that helped us measure it from the plot plan.
Remember we got the one for zone 6, I think from from that
That one was
PDMS
from the
software.
model, yes. But for
Yeah.
zone one, we didn't go into the model yet. So I'm trying
Yeah.
to remember if
Okay.
it was from the one that what they call them supply sent, or if it was what was measured from the plot plan. It was one of them anyway. So basically, you're using to calculate your surface area. I've just used pi r. This is pi r times L, but I think I need to revise this formula because actually someone has pointed out to me that it needs to be updated. So basically, the surface area calculation is just your regular surface area. So depending on the type of shape the equipment is, so there's no one answer for your surface area calculation. so so this one I think should be, I think it's cylindrical. If you're looking at a cylinder, you actually should be doing pi RL. I think yes. Yeah, I think that's where, but because this is a manifold system, I think this is correct. It's by RL. But if you're dealing with a vessel, because it is cylindrical and you still have caps at the end, you have to add plus pi 2 pi r squared to address the ones at the other end. So depending on the shape you're dealing with. So for example, now, okay, so it was this feed preheater exchanger that someone had pointed out, because I just assumed I'd taken it as a cuboid. So I basically I was looking for the surface area of the volume that we have in terms of the length, width, and height. But someone's looking at the PFD recommended that we should treat the feed preheater exchanger as a what do you call it, as a cylindrical vessel, in which case I think I'm just going to use pi 2 pi r squared plus 2 pi rl as the surface area. So the question now is which L should I use? Should I use the height or should I use the length? I guess I'll use the length because the length is longer than the height. So I'll update there. So basically, depending on what the shape of the equipment is, okay, in the case of the pumps, for the pumps, there's a requirement in the codes. I can't remember which of the exact codes. If you're dealing with pumps, you're basically just looking at the floor area, but you have to add 1.2 meters to each, that's 0.6 meters on each side for the length and for the width to take care of the motors and their extensions and all of that. So that's where this plus 1.2 is coming from. So there's no, you need to know what equipment you're dealing with for you to know which surface area you are using. And then in terms of the application rates, like I said before, if you're dealing with an equipment that is on fire, you would use a higher application rate typically than for the same equipment. So for example, for this inlet manifold system, when it's on fire, I'm using 12.3 liters per minute per square meter. But when it's being cooled, you see that I'm using 8.2. Same for the feed preheater exchanger. So depending on whether it's on fire or it's cooling, the application rate differs. And so when you're done with calculating, so you look at each scenario. So in this one scenario, I came up with 999.16 cubic meter per hour. But you need to also factor in 10% wind loss contingency. That's part of the design basis. The design basis requires that we do that. So because when you're applying water, when you're pouring water on your vessel, it's not going to just fall in a linear manner. The wind will also interact with it and blow some of the water away, and some of the water will be wasted. So we account for that and we put 10% contingency on it. So we've we've calculated this way. And so we look at the different scenarios in each zone. You look at if this vessel is on fire and the other ones are being cooled, and just go through all of the vessels. And as I had gone through at the time, but I'm still going to do and look at this a bit more with a bit more, what do you call it now? I'll look at it a bit more because someone had highlighted some of the equipment that we can tell from their shapes because we are trying to reduce the amount of water we're pouring. So this one is 997. This one is 1192. This one is the other scenario is 973, and last one is 924. So the one with the highest demand based on my initial calculation was 1192.104, and that scenario is when the I think the feed preheater exchanger is on fire. I think that's the scenario. Yeah. So that's going to be the governing scenario for this zone. So in my summary sheet, I've highlighted there that this is it. So the flow rate I calculated was 1192.104, and each monitor that we are bringing in is able to do 120 cubic meters per hour. So when you divide 1192.104 by 120, you're going to get 9 point something monitors, and you can't have 9.9 monitors, so it has to be 10. So when you get 10 monitors, you know that 10 monitors are going to give you 1,200 cubic meters. And then so I went on to do some line sizing. So I did the line sizing. So for the zone 1, because the header that is bringing water to zone 1 is not going to take 1.52 or something, it's going to bring 1,200. And so to do your line sizing is just the way you would do your line sizing as a process engineer. You need 1,200 cubic meters per hour to go through a line. The maximum velocity allowed in the line is 3.048 meter per second. And then so you're just using flow rate Q is equal to area times velocity. So you're going to divide flow rate by velocity to get your required area. And then you know area is pi r squared. You divide area by pi and find the square root for you to get your r. But the diameter is 2 times r. So that's all we've done to get to this point. But when you calculate, for example, in the case of zone 1, we had 15 inches. We know we are not going to get a 15-inch line. So we go up by size, because then we know that we are still going to be below the maximum allowed velocity. So we step up to 16 inches. So that's how I calculated my header size going to each zone, which is 16 inches in this case. So I'll take your questions at this point.
Oh, thank you for that, ma. It was part of my question.
Sorry?
It was part of the questions that I said I was there. The question that I put to ask.
I can't hear you. Miriam, can you hear?
I'm actually beside her, so.
Hello, ma.
Yeah?
Hello, ma. Can you hear me?
I can hear you now.
So, part of the questions that I put down was to ask you on how you got from your summary, how you got the flow rate. Explain
How I got the what?
The flow rate, the total flow rate.
Okay, so the total flow rate for the gas plant, right?
Yes, so for the first zone. For the first zone now,
Okay,
it's
for the first
1,192.
Okay, the 1,190. So you have to go into the spreadsheet. So the idea is that I won't put all of the details in the report. It's going to be someone that needs to know how I came about it. So when you need that further information, that's why the spreadsheet is in the appendix, so that you can go and look at it and all. But the main value, so for you that want to learn, whenever there's a calculation or something, you're not going to get the answers in the main body of the report. The main body of the report is actually aimed at someone that needs to take a decision. And you see there's an executive summary as well in the report. It's basically for someone that is too busy to go and be looking through spreadsheets and all of that. So pulled out all that information. But for those that want to learn, you need to start from the spreadsheet and go through the spreadsheet and then see, okay, so typically some people will hide their calculations because they don't want someone else to be able to do anything without coming back to them. But to be honest, I don't have that kind of energy. I like to put everything in there and all of that, so that if you have any questions, you deal with it, as in you look through and all of that. If I had enough time to do the report the way I love to do reports, I probably in the methodology would have also written out how I calculated the surface areas for individual things and all of that, but it's going to just make the report even lengthier and all of that. So, but in some cases, I've done that. But in this case, to be honest, we don't have enough time to go through all of that. So that's why if you want to get into the weeds, you're better off going into the appendix. That Excel sheet is really for a learner, someone that wants to learn how the thing is done. Then the actual report is more or less a summary for the people that are not as concerned about how it's done as it is for them to know what the results are and for them to run with it. So do you have any other questions?
Yes, from the summary, you said zone 4. Zone 4, then MRU train one area has the highest flow rate,
Yeah.
1,349 cubic meter per hour. But when I checked zone 4, from the sheets now, when I checked it, I didn't see any of the zones, like
So
any
you
of the
see
scenarios.
1440 for zone 1, for zone 4.
For zone 4,
Zone 4 is 1349.772801, right?
yes.
And so I've written, so that's for the MRU train 1 compressor package on fire. So if you
That's
go
what
to, okay, so if you go to zone 4, so MRU train 1 compressor package on fire, I think that should be scenario 4. Okay, so this is 1116. Okay, I see what you're
it's
saying. 1116. Okay, so that's an error from me, but I'm not quite sure how I got the one we what do you call it? I'm not sure where that came from before, but I'm quite sure I saw it somewhere for me to okay, or maybe okay, yeah, I think I didn't update that. No, but I showed up. I think I didn't update
because this one is the one you
summary.
sent now.
Yes, I think I didn't update the summary in front. Yeah, I think that was the problem. It was
okay, because if you don't update the summary and we are still leaving zone 4 as 1116, then it means that the zone.
Yeah. So anyway, I think I'm going to recall the IFR if it hasn't been issued, or will reissue for IFR anyway, because I want to do the calculations again based on the recommendation from some other
of the disciplines.
Well, nobody reviewed it at IT, sadly.
Okay.
Nobody reviewed it, sadly. Okay.
Okay, madam. Please, one last question from the line sizing, the calculation you explained.
I'm listening.
Yes, the line sizing calculation. So how did you get?
I can't hear you again.
Hello, ma.
Yeah, I'm listening now.
Yes, I said from the line sizing calculation you explained. Yes, please can you come again with the explanation on how you got the I think what was this? Yes, the diameter. The diameter calculation.
Okay, so it's just what you do as a process engineer anyway. So if you have the flow rates or whatever, whether it's crude, so the difference between your firewater system and your regular product system, condensate, gas, etc., is that instead of gas, you're using water, but the principles are similar. So in calculating the diameter of a pipe that has fluid going through it, you need to know what your maximum allowable velocity is. And when you do that, when you do the maximum allowable velocity, you now to get your flow rate, you divide to get your diameter, you divide the flow rate that's going through the line by the velocity. when you divide meter cube per hour per second, sorry, so you have to get the units to be in the same set of units. So you had meter cube per hour before, you have to convert that to meter cube per second. Because your velocity is in meters per second. So you divide your flow rate in meter cube per second by the velocity in meters per second. So that gives you the area in meter square.
Okay.
So you know area is pi d for a pipe. Area is pi d squared over 4.
Okay.
That's the area. So to get your d is going to be square root of 4 times area divided by pi.
Okay.
So you get that value in meters. Then you now need to convert back from meters to inches.
Okay.
Basically, that's what you're doing. That's what you're doing.
Okay. All right. I get now.
Okay. So if they haven't submitted the what they call it, what they call that thing now?
Okay, for
they haven't submitted
IFR.
the what case I think I would like to recall it. The Firewater demand and as well as the other one, the design report.
Okay. I'll find out.
If it can still be, or if they can recall it, even if it has been issued, so that we can update it and fix all of this.
Okay, that's the Firewater demand calculation, right? And the reports.
And the two documents are issued for IFR. If we can pull them up, I would appreciate it.
Okay.
Oh, I wanted to ask you, can you hear me? Hello?
I'm listening.
Hello, can you hear?
Sorry?
Yeah, well, so can you hear me? I wanted to ask you a question.
I didn't hear that. Is that Miriam?
Yes. I wanted to ask you a question.
Please go ahead.
Yeah, okay. So I wanted to ask, for the line sizing.
But can you increase your volume, please? Please increase the volume.
Can you hear me better now?
It is better now.
Yes, I wanted to ask you, there wasn't any margin added in the,
Sorry?
for the diameter. No margin was added. No, you calculated and then you took a recommendation.
I didn't hear you.
Can you hear me now?
I can hear you now. You said no margin was calculated.
I said no extra margin. I don't know if it's necessary, but
Sorry?
like additional margin.
Can you put it in the comments?
Okay.
Can you put your question in the comments? I can't hear you. Okay, Miriam, are you typing this in the comments?
Yes, in the chat.
Okay, please, we'll just wait for you to type it and I'll read it out and answer.
Hello, ma.
I can hear you. Have you dropped it?
Yes, she has dropped it.
Okay. All right. Okay, so is it necessary to add design margin to determine the recommended pipe diameter? I'm not sure I understand what your question is. Are you saying that should we have added the 10% before we determine the recommended pipe diameter? Is that your question? You can just type yes or no.
Yeah. Is it necessary?
I can't hear you. You can just type yes or no. Okay, so your question, yes, you. So remember what I was saying. The reason why we're putting the design margin, we're saying that when you in real life, when you're fighting the fire, the wind will interfere. Your water is not going to be falling straight. It's not going to just be falling because the wind is going to blow some of it away and all of that. So yes, it's important for you to consider because it's more or less you are more or less correcting for the what will be displaced by the wind. So you need to include that before you before you determine what your pipe, because you want all that water to be going through your pipe. So yes, you have to factor that in when doing your calculations. So does that answer your question?
Yeah. Yes.
All right. Do you have any other questions?
Can you hear me?
Okay, so can we
Miriam wants to type another question.
okay, please go ahead. I'm here for you.
Okay, then before that, I have another question, but I think it's not based on this demand, Firewater demand. So when I
Okay.
was going through some of the deliverables you sent, so from
Okay.
the safety equipment list, you listed out 9 safety equipments. So
Nine
that will be
safety
need,
equipment.
yes, nine. So, but on the data sheets, just 4 were captured. You captured just 4 equipments on the data sheets.
Okay, I'll need you
Hello.
I'll need you to but can we talk about discuss that separately?
Ma,
Is that okay?
can we what?
As in, can we discuss that after we are done with our discussion of Firewater?
Okay, ma. Yes, yes, ma.
Let's and if you can help with maybe send me an email, it would be nice. Okay, so okay, what do you mean by monitors? I think I'm going to leave. I'm going to let Omo Shaliwa respond to that one because I've given her the answer. So, Shaliwa, do you want to answer that question about monitors?
Ma, you can answer it.
But I told you now that I'm actually asking you because I want to be sure you heard what I said.
Yes.
Is
I
Miriam
have,
close to you?
yes, she is.
Okay, so can you show her? Can you give her? Can you show her one of the monitors that I showed you? But basically, Miriam, Firewater monitors are used to fight fire. So when you have a fire in a system in an area, there are different ways you can decide to fight the fire. You can decide to put what are called deluge nozzles or spray nozzles. So in the case of the spray nozzles, they are there, they are above the equipment itself. And once your deluge valve opens, you've piped all the way up to the you have a pipe that goes up to those deluge nozzles. And so once your deluge valve goes open, the firewater will run and go into the nozzles, and those nozzles will then begin to pour water on your equipment to extinguish the fire or to cool the equipment. So that's one way. But then for each vessel, that means you're depending on the spray angle of your deluge nozzles. I've done a design where we needed up to 200 and something deluge nozzles for the entire facility. And that, in my opinion, is a bit too much and all of that. So we need to, but that's not the major reason why. If you have congestion in an area, then there may be a good reason for you to want to put the nozzles, because the deluge nozzles can go close enough to the vessel to be able to work. But if you have enough space, the monitors are they're like they're easy to be. If a human being can also operate the monitors, But in this case, because it's a gas plant, we want to recommend that they should not be manually used. But essentially, monitors can be moved. They have I don't know, have you seen a fire hose before? I'm trying to use a fire hose as an example. Miriam, have you seen a fire hose before?
Yes, I have.
Okay, you can just say yes or no. Have you seen a fire hose before? You can type it, yes or no. Yes. So the monitors they are flexible like fire hoses. So they can move around, and you can, so your deluge nozzles, once you put them in, they are just stationed over a particular equipment, and they only work once your deluge valve is activated, and then the water rushes there. So for your monitor, yes, you can put it will be farther away from one equipment. So it is taking care of an area, or they are taking care of. So when we say that we want 10 monitors in the inlet manifold area, no monitor is going directly over, for example, the inlet manifold itself or something. We are stationing them a bit away, and so they can move around like hoses, and they have a father, they can, some of them can go as far as about 10 meters or 20 meters from where they are stationed. So you can use them for one equipment or the other, so they are easy to manipulate. But in this case, because we want them to be automatic, we would have positioned them in such a way that when they are spraying, they are able to maybe move around and hit this equipment, hit that equipment. So some of them are fighting the equipment that is on fire. The other ones are cooling the equipment that's around. So in our placing of the monitors, we have set them up so that they can help us fight the fire. And we want, in this case, we want them to be automated, and with the option of being able to be used manually as well, if the need arises, if we feel like it's safe enough for a human being to get there and go and use them. Otherwise, we'll set them up so that even from the control room, they can be operated, and they're basically, they are just for firefighting. So I think I'll just ask Shaliwa to please help me show you, and you can Google it actually.
Yes,
Just
yes,
Google firewater
we have
monitor.
Googled it already.
Okay, so the image that comes up is a firewater monitor, but the application is that it is used for firefighting. And you basically don't want to put people there if you don't have to put people. So do we have any other questions regarding fire water demand?
No, ma'am.
Okay, so I'm going to stop recording because I just want, and the reason why I asked you to let us move it is that I wanted this recording to be just for the fire water calculation record.